group, it's Mrs. Schaus. We're ready to talk about section 2.8, which is on inverse functions. Now, I recognize that the first learning target says find the composition of functions, which we sort of, just finished with. But this second piece down here, use the inverse function property, that requires the composition of functions, but then is related to the idea of inverses. We'll visit that in a bit. But I do want us to start out in thinking about inverses of functions. There are some pieces of terminology down here that I want to discuss, and I'm not going to write formal definitions to these. I want you guys to understand that you could certainly look up a more formal definition in your textbook if you wanted, but what I really want, I wanted these to be talking points so that we make sure we understand the concept of each of these. So first of all, what does it mean for a function to be one-to-one? Well, we might want to start out with a refresher of what does it mean for a relation to be a function? Well, you guys could probably give me a definition like a function means that each input is mapped to exactly one output or something like that, and that would be wonderful. That would be accurate. Here's an example of a function, y equals x squared. I know this is just a sketch and not a full-on graph because I don't have points actually plotted here, but that's the shape of the curve, and I want to use it again just as a little talking piece. So keep in mind, covering this up for a moment, keep in mind that this is a function because it passes the vertical line test. Any vertical line would only touch this in at most one place, right? Or exactly one place in this case. So that does in fact make it a function. But a one-to-one function, that means that not only does each input produce exactly one output, but also that each output only comes from one input. So let me try to see if I can help you make sense of that. If I were to plot the point x is 2, 2 squared would give me 4. Up here, let's say, that point would represent 2, 4. So 2 is, in fact, paired with just one output, namely 4. There's no other output for x when we use 2 as that input. However, there's another place over here, this point would actually be negative 2, 4, where there's an output, namely 4, that has two different inputs. Now, it's still a function, but that means that it's not a one-to-one function, okay? If I skip the idea of an inverse for just a moment and I look down here at a horizontal line test, horizontal line test can tell me a couple of things depending on how I want to word it, but one of the things I could say is rather than a vertical line passing through the relation in at most one point and telling us that the relation is a function, if a horizontal line passes through the graph in more than one place, what that tells us is that the function is not one-to-one, or in other words, that its inverse is not also a function. So I do have the idea of inverse here. What's an inverse of a function? Well, an inverse means essentially that you've interchanged the x and the y, the position or the role of the x and the y. All right, so if that's the case, you could say I'm using the horizontal line test to tell whether or not the original function is one-to-one, but I can also use it to tell whether or not the inverse of that function is itself going to be a function. Okay, so since this fails the horizontal line test, it is not a one-to-one function. It is a function because it passes the vertical line test, not a function or not a one-to-one function because it fails the horizontal line test. Okay, and then the last little piece we're going to talk about here is restricting the domain to produce a function. So what we're talking about, and we'll see it in an example in a bit here, is that you could choose to look at a function just for a portion of its domain. Let's say I look at just, this half here, to produce then a function whose inverse will also be a function. So in this graph, if I picked all x's that are less than or equal to 0, that portion of a graph would not only pass the vertical line test, but also the horizontal line test, and therefore its inverse would be a function. Okay, let's move on to some examples on thinking about finding inverse. So first of all, we've got some steps in finding the inverse of a function algebraically. If the function is written in function notation, so using f of x, we want to replace that with y. We're going to interchange x and y. After all, I mentioned just a moment ago that that's what an inverse does. It interchanges the x and y. We're going to resolve our new equation for y, and that will be the inverse. So to go back to function notation, we're going to replace y with f inverse of x. Let's practice that. Find the inverse of this function. Well, again, step 1 says replace f of x with y. Step 2 says interchange x and y. And step 3 says let's resolve that for the y. So I'm going to multiply by 2 on each side. That gives me 2x equals y squared plus 1. Subtract 1 from each side. So now I've got 2x minus 1 equals y squared. And lastly, I'm going to take the square root of both sides of the equation. That would give me plus or minus the square root of 2x minus 1 equals y. You guys know when you take the square root of both sides of an equation, you put a plus or minus sign out in front of it. However, step 4 says replace y with f inverse of x. Well, if I were to write f inverse of x here, I'd have a little bit of a problem. We know that square root functions open to the side like this. And so if I've got the positive root and also the negative root, that would give me a piece that sits down here, and that would not be a function. So in order to write this as a function, f inverse of x, I've got to pick one of the roots, either the positive one or the negative one. I'm going to pick the negative one. So I've got the square root of 2x minus 1 equals f inverse of x. This portion would not really be part of the graph, of course. And this is just a sketch of the parent function. It's not the actual function here. But I actually do want us to look at the function itself. So let's do that here. I'm going to try to let you still see this work, but now take a look at it graphically. So I want to begin with the original function that we had, which was y equals x squared plus 1 all over 2. And I want to make a little table so that we can plot some points of that, for that curve. Okay. So maybe I'll pick like a couple of negatives and 0 and a couple of positives and see what we get for our outputs. Light to come back on. There we go. All right, I'm going to start with 0. If I put 0 in here and square it, I get 0 plus 1. That's 1 over 2. A half is my output. Let's do positive 1. 1 squared would give me 1 plus 1 more. That is 2 over 2, or 1 as an output. And I hope you see that if I put a negative 1 in here and square it, I'm going to get that same output. Similarly, when I put in a 2 squared, I get 4, and 1 more, that's 5. I could write this as 5 halves, but that's the same thing as 2.5 if you prefer to see it that way. And if I plug in a negative 2, I'm going to produce the same output. So let's go ahead and plot these few points so that we can see what the curve looks like. At 0, we were up a half. At 1, we are at 1. At 2, we are up 2.5, so about there. And similarly here back, negative 1 up 1. And when I'm at negative 2, I was up 2.5, so about there. So here is the shape of that curve, which shouldn't surprise me that it's a parabola because, I've got this x squared variable there. All right. What I want you to think about now is the new function that we described, f inverse of x, equaling the square root of 2x minus 1. So again, I'm going to make a table of values for that. What if I put, I don't know, a negative 1 in here? If I put negative 1 into that function, I produce negative 2 minus 1 more, negative 3 underneath the radical. Oh, can't have a negative under the radical. All right, how about if I put 0? That's still going to leave me with that negative 1 under the radical. So what is the first place that I can, sort of start, a value I can put in here for x where I produce something that's not negative, where I produce 0 essentially, right? That happens at a half, because 2 times a half would give me 1, And 1 minus 1 would give me 0, the square root of which is 0 itself. And so I only want to pick points that are bigger than a half. How about if we pick something like 1 and 2 and see what we produce there. If I put 1 in here, I get 2 minus 1, which is 1. The square root of that gives me an output of 1. If I plug in 2 here, 4 minus 1, that gives me 3. So take the square root of that, I get the square root of 3, which according to my calculator is approximately 1.7. So let's plot those points. A half 0 sits here. 1, 1, oh, they meet up at that point. And 2, 1.7, about right there. Now, maybe I should have put in 3 or 4 so I could get a better feel for this, shape of the curve. But I do, again, know that this square root function has this shape to it. So I think even with those few points, I can get a feel for what's going on there. Now I want you to see that if I cover up this half of the original graph, those look similar in some way. In fact, they're a reflection of one another. So hopefully from Algebra 1 or 2, you remember that inverses are connected graphically in the sense that they are reflections of one another over the line y equals x. That's actually why they're meeting up at this point 1, 1, because at the point 1, 1, the y and the x are equal. Let me go ahead and draw in a dashed curve here at the line y equals x so that you can, again, sort of visualize that those really are reflections of one another through that line. Now, in order for this to be the inverse of our original function, again, that meant that I wasn't considering the piece here. So the question about how can we restrict the domain so that the inverse is also a function, that tells me that I want to look at this original function, but only for x's that are greater than or equal to 0. So that is how I would restrict the domain so that I can make, again, my new f inverse of x truly be an inverse of the original f of x. All right, I want us to practice a little bit more in finding inverses algebraically. So let's continue on with these problems. Remember that step 1 is to replace f of x with y. Step 2 is to interchange x and y. Step 3 is to resolve for y. So I'll multiply by 5 on each side. Add 7 to each side. I'm running out of space, so I'm going to come up over here. I would need to divide by 3 on each side. So 5x plus 7 over 3 equals y. Once I have the equation solved for y, remember that I can use function notation again to say the inverse equals 5x plus 7 over 3. No need to restrict the domain for that particular problem. All right, let's take a look here at our g of x. Again, I'm going to replace that with y. That's our step 1. Step 2, interchange x and y. Now step 3, we're going to resolve for y. This time we need to undo a cube. We undo cubes with cube roots. So I've got the cube root of x equals, on this side if I do the cube root of something cubed, again since they undo one another, I would just have the quantity y plus 4. And in the last step, I'm going to subtract 4 from each side. Now I don't really like to put the f inverse on the right hand side. I'm going to switch it and put it on the left. Oh, and I really shouldn't use an f. This function is defined as g. So let me use g inverse of x equals the cube root of x minus 4. Okay, so there's a couple algebraically. The last piece we need to look at together is verifying when two functions are given and we're asked, are these two actually inverses of one another? How can you tell? Well, some of you might say, well, that's easy enough. Just take the first function and go through the process we did just a moment ago. Rewrite that as y equals 3x, interchange the x and y, resolve for y. You certainly could do that, but there's another way. there's a property called the inverse function property. And what it says is, if you calculate the composition, there's that word we talked about at the very, very beginning. We just studied compositions. If we calculate the composition in both directions, f of g of x and g of f of x, and in both cases, we end up getting x as a result, then we know that the functions are inverses of one another. Now, your textbook doesn't say f of g of x equals x and g of f of x equals x. It says f of f inverse of x equals x, and f inverse of f of x equals x. That means the same thing because we're claiming that f of x and g of x are inverses of one another. Okay, so these two mean the same thing, just different notation. All right, so knowing that that is our inverse function property, again, read about it in your text if you'd like to. Another take on it, a little more. Let's give it a run, see what happens. So I want to start by calculating f of g of x. That means I'm calculating f of, let's see, g of x is x over 3. So if I plug in x over 3 here, now I take my f function, and where I see x, I put x over 3 in its place. So I'm going to do 3 times x over 3. And what do I get as a result? What do I get as a result? Well, these cancel, and so I just end up getting x. Cool, easy enough. Let's try it in the other order. So I'm going to calculate g of f of x. That means I'm calculating g of, let's see, f of x is 3x. So I'll put a 3x in here. And let's see, that means that in this function g of x, I'm going to write 3x in place of x, and then it's over 3. And now those 3's cancel each other, and so I just get x. Notice that the work looks differently here than it does over here. Don't just assume that because I see a multiply by 3 and a divided by 3 that you're necessarily always going to get inverses of one another. It does not always work quite so simply. These are pretty basic ones. But since I do get x here and here, we can say they are inverses. Okay, this asked me to verify. So basically it was saying they are inverses, and I want you to show me that. But the problem could say determine if they're inverses of one another. So it could be that you don't get that they equal x each time, and you can say, no, these are not inverses of one another. Let's see what happens here. So I'm going to calculate f of g of x is 1/2 x minus 3. Let's see what we get. So I'm going to, in the f function, wherever I see an x, I'm putting this expression in its place. That would give me 2 times 1/2 x minus 3, and then plus 3. Now, if you're expecting this to work, it would be real easy to say the 2 and the 1/2 cancel each other, the -3 and the +3 cancel each other, so I really do just get an x. Oh, but be careful here. This 2 means that I have to distribute through here. So that would give me x minus 6 plus 3 equals not x, right? It equals something other than x. It's not equal to x. Now, if either one of them is not equal to x, you can stop and say, these are not inverses. However, sometimes the first one will work, and it's the second one that doesn't work. So be careful that if one works, you do have to show the other direction to be able to say, check, yes, they are really inverses of one another. All right, I hope that helps you folks out when you try to get started with the exercises on the section. We'll talk about it some more in class. Well, virtually anyway. Take care and have a great day, folks. I'll talk to you soon.